Bismillahirrahmanirrahim. My name is Dr. Muhammad Alam Zifan, and I would be teaching you the course of thermodynamics. This is our first basic course of thermodynamics, and that is in our mechanical degree. Uh, in initially lecture, we would be discussing the basics of thermodynamics, its related definition, the basic definitions. We would be also looking at the property of the pure substance. After that, we would be looking at the heat and work definition and heat and work in thermodynamics. Once we are familiar with all these terminologies, all these terms, we would be finally looking at the first law of thermodynamics and second law of thermodynamics, and obviously its application. So our whole course would be something like this. In today's lecture, we would be defining some basic terminology, and that would be some basic terminology that would be used in our thermodynamics course. So first thing, what is actually a thermodynamics? What is thermodynamics itself? Thermodynamics. So term mean heat and dynamics mean motion. So that means like heat in motion. So if you are looking at, let's say, a Greek word, and that means like dynamo. So that means like dynamo mean power. So if I'm combining all these definition or all these words, so that would make us a proper definition of thermodynamics, and that is heat in motion that would produce power for us. So thermodynamics is concerned with the heat in motion, and that heat in motion which produce power. So in our course, we would be concerned with the mathematical model of a real world. So whatever we have talked about, like we are talk about like heat, we have talked about like motion, heat in motion, and that we have talked about the power. So we would be looking at how much heat is it, how much it would produce power, and obviously the relationship between them heat and obviously the power. So we would be looking at the mathematical model of that real world. And obviously, in order to go for the mathematical deduction of these things, we need to define some precise definition of the basic concepts. Before we go towards the actual basic concept, let's limit our thermodynamics itself. In thermodynamics or in classical thermodynamics, we would be concerned with the Continuum model, or what we call it as the average model or average information model. You might know like there are the molecules or matter, they are composed of many molecules, and we are talking about the molecule at the microscopic level. Uh, and yes, we are using the techniques of statistical mechanics and kinetic theory, but for our engineering purposes, it is not likely that we would be using the microscopic level or the molecular level of that concept, but we would be using the average information of that one. And that by average being like we would be using the macroscopic description rather than the microscopic description. Why we are not concerned with the microscopic? Like if I'm talking about the any microscopic example, for example, 1 cubic millimeter of the air, it contains 10 to the power 16 molecules. And if I'm concerned with the position, velocity, force, pressure of these all these things, so definitely I would need so much of the variables, so much of the equations, and obviously addition, subtraction of all these things. So doing that will be obviously a little bit hectic job for us. So in our classical thermodynamics, we would definitely not look at the microscopic level, but we would be looking at the macroscopic level, or the average information, or the Continuum model. So in classical thermodynamics, we are concerned with the continua, and we are concerned with the macroscopic information. By saying so, let's move forward to the basic definition, and that basic definition of different terminology that would be used in the thermodynamics. So the first concept is the concept of the system. So what is our system? So anything under consideration is called as a system, and that any other thing which is not under consideration or anything beyond that consideration would be called as the surrounding. So we have got anything which is under consideration, we call it as a system, and which thing which is not under consideration is called as the surrounding. The system and surrounding, they are, or the system is surrounded by a boundary. So that means like system is distinguished from the surrounding using a system boundary. That system boundary can be a physical boundary. That system boundary can be a non-physical boundary. For example, let's say for if I'm saying like it is an open system, so that mean like open mean like that it is the something molecule which actually going out of this imaginary boundary would be actually going from this open system to the outside, and that's what we call it as a, this boundary is an imaginary boundary. Or let's say if I say like it is a closed system, if I'm saying like this boundary is what we call it as the boundary of the system, and that's we can say like it was an imaginary boundary. Yes, this boundary of the system is a physical boundary. So that means like it's the boundary itself of the system can be a physical boundary and can be a non-physical boundary. It can be an actual boundary, it can be an imaginary boundary. But every system is surrounded by a boundary, and also the boundary move with a system. So it does not mean like if the system is moving forward and the boundary remain there, so it will not be there. So obviously the boundary move with a system. So defining the system and surrounding and the boundary, we have got three type of a system: open system, closed system, and isolated system. An open system is a system in which both mass and energy, or the both matter and energy, is exchanged with the surrounding or is exchanged with the environment. So this is an example of an open system. If this system is actually exchanging both mass and energy with the surrounding, so that means like it is an open system. Now let's say we put a lid on that system, and if I'm putting a lid, that a solid lid, that means like now the system cannot exchange mass with the surrounding, but it can still get exchange the heat or coldness with the surrounding. So that means like it can still exchange the energy with the environment. So that means like it's a closed system. So an open system which both mass and energy is exchanged with the surrounding, while the closed system in which mass is not exchanged with the surrounding, but only and only energy is exchanged with the surrounding. And isolated, now if I put thermal lagging on this one, and if I say like there is no energy even leaving the system, so that is an isolated system. So an isolated system neither exchange energy or neither the mass with the environment. An open system is also called as the control volume system, and closed system is also called as a control mass system. So go through these examples and you will understand what's a closed system and what's an open system. So that's an open system, both mass and energy was exchanging. That's a closed system, so we have got only energy exchanging with the system, not the mass, and so on and so forth. Now what is a state, or the concept of the state? State is defined by set of measurable property sufficient to determine all other property. So if I'm saying like today is a hot weather, or the water is cold, or I'm moving fast, or I'm moving slow, something. So that means like this hotness, this coldness, this faster, this slower, these should be defined by some measurable property. By hot mean like the temperature of the substance or the temperature of the weather would be greater. By cold would mean like the temperature would be less. So that means like this, the measurable property is the temperature. So if I can measure the property, and that is the temperature property, so that means like I can say like it is the, I am defining the state. And let's say if I'm moving fast, I'm moving slow. That means like my velocity is actually sorry for that. I would be using not v for velocity, but I would be using s for velocity. So that means like my velocity is actually less. So that means like I'm moving less. I'm moving slow. If my velocity is greater, so I'm moving faster. So that means like the state is defined by set of measurable property. Once I define the if I measure the properties, then that means like I define the state of the system. For a fluid system, for a simple fluid system, I would be using simple property like pressure, volume, and temperature. But for me more complex system, I would be using many other properties as well. And yes, you can go through the example of electrical system. You can go to the example of any other system you can consider. By property, we say like we have got two different kind of a property. One we call it as the extensive properties, and one we call it as the intensive properties. Extensive properties are called as the additive properties, while the intensive properties are non-additive properties. For example, if I'm saying like if I have got a cube, let's say, and if I say like I divide a cube in half, something like this, so the volume of a cube would become half. So that means like the volume is an additive property. That means by dividing, it can divide. Same thing like if I've got, let's say, a solid mass something, and if I just cut it into half, the mass of the object would be half. So that means like mass is also an extensive property. But now let's say, what about the if I say like a cube? What if I say like I divide the cube into half, and what if I just check the pressure in both of the area? So let's say pressure A and pressure B. So that means like both of the pressure would be same. If I just say like I just want to find the temperature at this half, and I want to find the temperature at this half, so that means like the temperature would be same as well. So that means like the property does not depend on the matter or the quantity. That is called as the intensive property. So temperature and pressure, they are called as the intensive property. So the property which are additive property, they are called as extensive property, and the property which are the not additive property, does not depend on the mass or matter, they are called as the intensive property. Now any property extensive property per unit mass is called would be called as the specific property. What I mean to say, like volume per unit mass, or if I say like the volume per unit mole. So that means like if I'm specifying an object, like how much volume would be in 1 kg of mass, how much volume would be in 1 mole of a substance. So if I'm specifying something, so that become a specific property, and specific property again become the intensive property. So the specific property are also the intensive property, because volume per unit mass, if I'm saying like that is 1 over rho density, and density itself is an intensive property. So that means like specific property are intensive property because they do not depend on again now on the mass. That means like we are saying like per unit mass or per unit mole or something like this. So specific property are again the intensive property. So the property of a simple substance, simple system are uniform throughout, while for the complex system, yes, we are looking at the complex scenario of it. But it is definitely important to note that the properties would describe the state of the system only and only when the system is in equilibrium. If you can check it up there, we say like the system is defined by set of measurable property. So the properties can only define the state of the system when the system is in equilibrium. So let me give you an example. Let's say, For example, I've got a bucket of water, and let's say it's a half full. Let's say, for example, a bucket having a volume which is half. But yes, I've got a tap up there, and the volume is still adding, or if I'll say the water is still adding to the bucket. So in that case, I cannot say like the volume is half, because the water is still flowing into the bucket. Or in other words, if I'm saying like another example, if there is a hole in a bucket and there is the volume is actually moving out of the system. So sorry for that. So if there is a hole in a bucket and the volume is moving out of the system, so I cannot define the volume of the system unless and until it is in equilibrium. So that, having said that, again I'm saying like the properties can only describe the state of the system when the system is in equilibrium. So now that's vice versa. In other words, the equilibrium is the condition in which the properties are unchanged and have got the definite value. So the system, state of the system in which the properties have got the definite and unchanged value, as long as the external condition are unchanged, are called as the equilibrium state. So in equilibrium state, the properties does not change its value. We have got the mechanical equilibrium, we have got the thermal equilibrium. In mechanical equilibrium, we would be talking about like the pressure equilibrium. In thermal equilibrium, we would be talking about the temperature. Then we have got the chemical equilibrium, in which we are talking about the reactions and the products, in which the product are definitely the forward reaction is equal to the backward reaction. So we are talking about different equilibrium condition, and we are talking about different properties in that equilibrium condition. The concept of the process. Now, if the state is changing, the state of the system is changing, then it is undergoing a process. So if the state of the system is changing, it is undergoing a process. So the state is defined using a properties. So that means like if the property of the system is changing, we are having a process. The succession of state through which the system passes define the path of the process. We will come back to it later on. At the end of the process, in which we are changing the state of the system or properties, if the property has returned to its original value, then the system is undergoing a cyclic process. So if I'm leaving from state A, going towards state B, and then I'm coming back to state A, so that means like I have not changed the property, or the property has returned to its original condition, original value. So that means I am undergoing a cyclic process. Now, having all these definition of the process, the state, and the equilibrium, we have to introduce one more concept, and that is the concept of quasi-equilibrium process. I did say like the state is only and only defined when there is in there when the system is in equilibrium, or the properties are not changing. Now, if the properties are not changing, so how I am undergoing a process then? So if I'm undergoing a process, then the properties will be changing. Now, if the properties are changing, then the state would be not defined. So one way or other, the state cannot be defined when I'm going under a process. And if I'm having a process, then the state is not defined. Now we would be having another condition, and we would call it as a quasi-equilibrium process. What is actually a quasi-equilibrium process? A quasi-equilibrium process is sufficiently slow process that any intermediate state can be considered to be in equilibrium. So let me say like, when I say like the system is in equilibrium, if I'm saying like let's say for example, I say like the volume is half, or the I've got the bucket and the volume total volume occupied by the water in that bucket is half. So I can only define I say like when the system is in equilibrium. But what if I've got a small hole in that bucket, and that mean like I can actually get a drop of water after 5 minutes, and that drop of water is again, if I'm saying like very small drop of water, so that mean like the volume apparently is changing. We have got the volume which is actually getting out of the system, but for, if you can imagine, for that small, for that interval of time, which is actually I said like 5 minutes, the system was in equilibrium. So that means like the system was considered to be in equilibrium in that 5 minutes, and I've taken that delta V after 5 minutes, and then again that system again become in equilibrium. What if this volume is very small? So that means like if I'm saying like volume minus delta V, and if say like that delta V is sufficiently so small that if I'm subtracting this volume from the system, and if I'm adding this volume to a system, it does not change anything, or the state of the system is not changing so much. This kind of a system would be called as the quasi-equilibrium system. You can look at the definition of the thermal equilibrium as well. So if I'm saying like I have got a temperature of the room as 35 degrees centigrade, and after 2 hours, let's say for example, I've got a temperature of the room as 35 point, let's suppose 2 degrees centigrade. Make sure this is summertime, so 35.2, 35 is normal temperature over here. So 35 and 35.2 after let's say 2 hours. So that means like for change, if I'm looking at the change for 1 hour, that change can be taken as let's say zero point 0.1. So I'm only changing zero point 0.1 degree centigrade in 1 hour. If I'm looking at let's say half an hour, so that means like for half an hour would be changing my temperature as 0.05 degree centigrade. For let's say for quarter, so I would be looking at 0.0025, and so on and so forth. So that means like when my interval is small, so the system is considered to be in equilibrium. So what again I'm saying like it is sufficiently slow process that any intermediate change or state, I say like any intermediate change delta V plus and that is in a temperature as well, are considered to be in equilibrium. So what is actually now the advantage of that thing? So now the advantage is I can now simply define the state of the system. Defining state of the system by moving very small steps, and I can even undergoing a process. So the state of the system that participate in a quasi-equilibrium process can now be described using very small number of macro parameters. And for a system in equilibrium, for example, P, T, V, we can actually define very small equilibrium. For quasi-equilibrium processes, we have got the example of isochoric process, isobaric process, isothermal process, and adiabatic process. Um, and that means like these processes are considered to be the in equilibrium. I said like we would be coming to this one. So that means like now I can define the state on every small step. If I'm saying like I'm changing volume from let's say V1 to V2, so that means like I can go from V1 to V2, and on each and every steps I can define the state of the system, because each and every step was considered in equilibrium, and I can define each and every step now, and I can define the path of the process now. Why we would need it? Definitely, I'm looking at the top definition right now. So in our thermodynamics, we were concerned with the mathematical model of a real world. So I said like we would be concerned with the heat, we would be concerned with the work, we will be concerned with different other kind of energies. So if I'm saying like heat, and that is heat in motion, so I can now define how much heat would be, how much work would be done by defining the system, by defining the state, by defining the equilibrium, by defining the process, and by defining the quasi-equilibrium process. And by doing all these things, I can define the equation of the state. So the first equation of the state we are familiar with, and you might have done in your previous classes. Um, so the first definition of the equation of the state, you have done the equation of the ideal gas, and that was actually PV is equal to RT. This was the definition of the equation of the state of the ideal gas. So that means like we are relating the pressure, we are relating the volume, we are relating the and we are relating the temperature in one of the equation, and we want to find the mathematical model of an ideal gas. We would be looking at the equation of the ideal gas later in the other part of our lecture, but I was actually trying to finish this lecture by the equation, and why we need to define the state, and what would be the benefit of defining the state of the system. So by defining the state of the system, we would be defining the equation of the state, and obviously equation of the state of different condition. I hope you understand that one. If you have got any question, you can actually post in your classroom, and I would be able to answer that one. Have a nice time. Thank you very much.